All right, so here we have a diagram of an exciton. So here we have, here if you say that this is an electron and a photon comes in and it hits the electron, it absorbs the energy of that photon. The electron goes up to a higher energy level. And what happens is that because once the electron has escaped, it leaves a positive hole. And positive hole and a negative electron that is in the high energy level, there will be a Coulomb attraction between the hole and the electron. So you've got an incoming photon that produces a hole and an electron. And whenever the Coulomb attraction is stable, it produces a bound state, and that is the exciton. And it is similar to a hydrogen atom where the proton is the nucleus and the electron is orbiting it, and you end up with a bound hydrogen atom. And the electron can fall back into one of the holes, and when it does fall back, then it will release a photon, and we call that a metastable state.
Now this looks very exciting. A direct image of an electron orbit in an exciton is a first, say researchers, 16th of May 2021. Oh, so you've reached the limit of what you can view on Physics World without registering. Okay, hold on, just wait, hold on. All right, now that I've logged in, after having logged in with 2 attempts, right. So, for the first time, researchers have captured an image of an electron orbital probability cloud within an exciton. Keshav Dani and colleagues at Japan's Okinawa Institute of Science and Technology Graduate University produced the image by kicking electrons out of their orbits using tightly controlled laser pulses and then measuring their trajectories with an ultra-precise electron microscope. Their results could lead to a new understanding of exciton properties that have long evaded physicists. Now, when an electron within a semiconductor absorbs a photon with sufficient energy, it will be excited to a higher energy level, leaving behind a positively charged hole. Because when the electrons escape, there's less electrons, meaning there's less negative charge, leaving a positive charge. And because there's no more electrons, there's a hole there. So that's why it says positively charged hole. Due to their mutual attraction, both particles will then briefly orbit each other, creating a neutral quasi-particle called an exciton. So now you know what exciton is. Excitons are key to the operation of semiconductor technologies, but so far they have proven extremely difficult to study. Not only can excited electrons fall back into their respective holes within just picoseconds. Pico is 10 to the minus 12 seconds. The quasi-particles can also be easily broken apart. As a result, key exciton properties, including their momenta and the characteristics of their electron hole orbits, have only been described theoretically. In their research, Danny's team introduced a new setup which allowed them to image these orbits directly. To do this, they first used a laser pulse to generate excitons within a low temperature 2D semiconductor, an atomically thin material where excitons can last for a relatively long time before electron hole recombination. With a second pulse, they then fired extreme ultraviolet photons at the excitons. This kicks the electrons into the vacuum of an electron microscope, which uses the wave-like properties of electrons to produce images at subatomic resolutions. By measuring the angles and energies of these displaced electrons using the microscope, the researchers could then determine their positions within their original excitons at the exact moment before they were kicked out. The process is comparable to the high-energy collisions carried out at particle accelerators. From the trajectories of the particles produced by collisions, physicists can deduce the nature of particles before they are smashed apart. By making measurements over many cycles of exciton production and destruction, Danny and colleagues could gradually build up images of the wave functions of electrons within their exciton orbits. These mathematical relationships relate to the probability of finding electrons in a given position when observed according to Heisenberg's uncertainty principle. In a striking image, Denny's team could clearly see the 3D wave function or probability cloud of an excited electron within its orbit around the hole. The ability to visualize internal orbits in this way could give researchers unprecedented control over the properties of quasi-particles, potentially leading to advanced new quantum technologies and exotic new states of matter. The research could also lead to a better way of studying other composite particles such as hadrons, which are made up of quarks.